Good afternoon. Welcome you to the High Performance Architecture webinar series. My name is Renae, Associate Professor at UNSW School of Building Environment, the convener of the High Performance Architecture Research Cluster. Before we begin, I would like to show my respects and acknowledge the Bidigo people who are the traditional custodians of the land on which this meeting takes place, and to elders past and present. This is the first High Performance Architecture webinar series this year. The speaker is Scientia Professor Santamouris, the Anita Lawrence Chair in High Performance Architecture at UNSW School of Building Environment. Professor Santamouris is the Editor-in-Chief of the Energy and Buildings Journal, and was ranked as the world's top-cited researcher in the field of building and construction. In today's webinar, Professor Santamouris will present recent progress on mitigation technologies. If you have any questions during Professor Matt's talk, please put in the chat, and Professor Matt will answer your questions as many as possible at the end of his talk. Also, just a note, this talk will be recorded. We would appreciate you switch off your microphone or video if you do not wish to be seen in the recording. Matt, over to you.
Thanks so much, Lan. May I share my screen? It's so nice to see so many friends here attending the conference. Friends from Mexico to Hong Kong, from United States to Korea and Malaysia, from everywhere. Welcome. We will discuss today about the recent progress on urban mitigation technologies. And why is it not moving? Okay, this lecture will, let's say, have three parts. During the very first part, we will try really to explain the main, let's say, characteristics of urban overheating. The magnitude of urban overheating, the existing studies, and the association of global climatic change with regional climatic change, and everything that has to do with, let's say, urban climatology. In the second part of this lecture, we will discuss about the impact of urban overheating on energy, health, environmental quality, survivability. And in the third part of this lecture, we'll discuss about mitigation, which really are the more important and the most important mitigation technologies, which is the potential of these mitigation technologies, and which is the state of the art regarding the implementation, let's say, in the world. So let's start. Is it urban overheating a serious problem? Yes, it is a very serious problem. According to a very recent study, there are about 13,000 overheating cities around the world. 1.7 billion people lives under severe overheating. And compared to the conditions of 1980s, there are 3 times more overheating, during, let's say, the last period. Also, we have almost 118 billion overheating man-hours, let's say, in the world. So it is a very serious problem. Regional climatic change together with global climatic change are among the most important, let's say, environmental problems we are facing today. What is urban, let's say, overheating? It has to do with the higher temperatures in specific parts of the city, usually in the areas with higher density, higher anthropogenic heat, and higher solar radiation absorbed and stored there. And this is a very documented phenomenon. It is the more documented phenomenon of climatic change. Do we have enough evidence and proofs about, let's say, climatic change, regional climatic change? Of course. There are more than 450 cities where data experimental data are available. I'd like to show you data from Asia and Australia, where you can see that the average, let's say, magnitude of urban overheating is close to 5 degrees, but there are cities which present, let's say, an overheating magnitude over 10 degrees. So it is a very well documented phenomenon. And unfortunately, it's not just the increase of the temperature in our cities. It is much more than that. It has to do also with the increase of the duration of hot spells. If we try really to plot the hot spells above 37 degrees, the red bars, or above 40 degrees, very serious hot spells, the blue bars, you will see that during the very last years, there is a tremendous increase of the hot spells. But it's not just the increase of the temperature and the increase of the duration of the hot spells. It's unfortunately more than that. It has to do also with the increase of the magnitude and the frequency of urban overheating. If we plot, for example, the number of heat waves with temperatures above 37 degrees during, let's say, the last 100, 120 years, you will see that during the very last years, there's a tremendous increase of, let's say, the frequency and also the magnitude of heat waves. So urban climatic change, it has to do with the increase of the temperature, in our cities, the increase of the duration of hot spells, and also the increase of the magnitude and frequency of heat waves. Once this is defined, then we have really to understand, let's say, the characteristics of urban overheating. It's not so simple. You can say, for example, that the temperature in the city is 5-6 degrees higher than in the surrounding, but this is not enough really to understand the science and the engineering of the problem and propose solutions. So we need really to go in depth, understand the phenomena, and at the same time really have a very good knowledge and plan, all possible, let's say, solutions to, let's say, face the problem. This can be done through experimental techniques or through numerical techniques. Numerical techniques, which have been developed really during the very last years, for example, let's say, mesoscale modeling allows us to have a very good understanding. For example, you see in this graph, the, let's say, temperature distribution in Sydney, where you can understand that in the eastern part, which is next to the coast, temperature is much lower because of the sea breeze, while in the, let's say, western part, temperature is much higher because of the proximity from the desert. So in a distance of about 50 kilometers, we have a temperature difference of about 10 degrees. Once we understand the reasons and the characteristics of urban heat island, then we can plan, let's say, our solutions and our, let's say, response to the problem. If we don't understand it and we, let's say, face the problem, or we, let's say, plan based on empirical, let's say, knowledge, I'm afraid that we don't have results. Another important issue, it has to do with the association of global climatic change and regional climatic change. What is happening, for example, regarding the magnitude of the urban heat island during heat waves? I will show you the results of two cities. In Sydney, during heat waves, the magnitude of the urban heat island is increasing by, let's say, 5 degrees. So we have, let's say, an increase of the magnitude of urban heat island up to 5 degrees because of, let's say, the synergetic reaction and action between the urban climatic change and also the global climatic change. So these two phenomena, when they work, in a synergetic way, increase the temperature of our cities more than what really happens during the reference days. The same happens, for example, in Athens, Greece. You can see, for example, the magnitude of the urban heat island in specific parts of the city during, let's say, the non-heat waves and during, let's say, the heat wave. You can understand that really it is much, much higher, the magnitude of the urban heat island, during the period of heat waves. So this is a serious problem, given that we expect a tremendous increase of the frequency and also of the magnitude of heat waves in the future. What about the impact? Of course, higher temperatures in our cities may have a very specific impact on energy, may increase the energy consumption for cooling, for example, may create a serious problem on thermal comfort, may increase the concentration of pollutants, may, let's say, have an impact on health, heat-related mortality and morbidity, may affect the economy or the sustainability and vulnerability of the population. Do we have enough evidence and knowledge about the real impact? Yes. During the last, let's say, 10, 15 years, we have collected a lot of real experimental data that document really the impact of urban overheating on our life. And let's start with energy. Urban overheating is affecting really the energy supply and the energy demand. How is affecting the energy demand? It is evident. Higher temperature means higher demand for cooling. And this means, of course, that perhaps we may have less energy for heating, which is not exactly the case. On the other hand, urban overheating is affecting very much the energy supply. Why? Because it increases the peak electricity demand. So it obliges utilities to build additional power plants to satisfy the additional demand during some days or some weeks per year. This increased tremendously the, let's say, the cost of electricity, because power plants have to operate just for some, let's say, days per year, and this means that they have to be maintained during the whole year, which increases the cost. On the other hand, we have a lot of power disruptions. We have, let's say, a higher demand during, let's say, the peaks. We have increased losses and many other things. Let's try to be a little bit more, let's say, quantitative. Do we know how much is the energy increase because of the urban heat island? Yes. By collecting data from more than 100 cities around the world, the average, let's say, energy penalty per square meter of cities is close to 2.3 kilowatt hours per square meter. Or if you like, the energy penalty per square meter of city and per degree of temperature increase is 0.7 kilowatt hours per degree and square meter. If you like to report it per person, it is close to 230 kilowatt hours per person per year. And also, if you like to report it per person and degree of temperature increase, it is 78 kilowatt hours per degree and person. Of course, these values may change from city to city, but these are really the average values we have collected. A very recent study that we have performed together with my colleagues in Korea, that they follow this, let's say, lecture, which really involved the real, let's say, energy consumption of buildings associated with the real overheating in, let's say, Seoul, shown that because of the overheating, the energy consumption of the buildings for cooling was, let's say, up to 1.8 kilowatt hours per square meter higher than, let's say, the other buildings. So there is a very important, let's say, penalty which is imposed in our buildings because of the urban overheating. And this brings us to the major problem we may face in the future, the energy consumption for cooling. How much is the energy consumption for cooling in our days? Very low. Very low. It's not so high. Heating is the main energy consumption. But what about the future? Which are the drivers that increases the energy consumption? First, the, let's say, increase of the temperature. Second, the increase of the population. Third, the tendency to increase the floor area per person. And also we have to consider that we may have in the future air conditioners of higher, let's say, efficiency, and also buildings of higher efficiency. When all these, let's say, parameters are taken into account, and we consider, you know, a low development scenario for 2050, in this case, the increase of the cooling demand will be of the order of magnitude of 320%. But once we consider an average development scenario, which is more probable, the increase of the cooling demand will be as high as 750% compared to 2000. And in case we have a very high development scenario, the increase will be of the order of magnitude of 2,270%. When uncertainties are taken into account, these numbers really are skyrocket, and we may have a tremendous energy increase for cooling. According to recent studies, just one, let's say, city of, let's say, India, Mumbai, may present in 2050 higher energy consumption for cooling than the whole United States. You understand the implications which are associated with such a high demand for cooling, which kind of sources we will use, how many new power plants, which kind of fuels we will use it, what about pollution, what about emission, what about the cost, and all these specific issues. A part of the energy impact of urban overheating, higher temperatures in our cities have a serious impact on air pollution, and mainly on the concentration of the atmospheric ozone. Ozone, ground level ozone, is a toxic gas, is a killer. Almost 87% of the episodes of high ozone concentration is because of urban overheating. And actually, we know, for example, that it is accepted to live under 110 units of ozone, which in my opinion is quite high. But unfortunately, in our cities, we have more than 300, let's say, units of ozone, which is very high and 3 times higher than, let's say, the threshold. A recent study collecting data from about, let's say, 100 Chinese cities shown a tremendous increase of the ozone concentration during the very last years. Unfortunately, the forecast for the future shows a tremendous increase, let's say, of the ozone because of, let's say, the future developments. This increase may be as high as 400%, I hope not, or as low as 20%, but it will be really high. So a serious problem that is associated with urban overheating, it has to do with the concentration of ozone. But it's not just that. We know very well that during, let's say, the high temperatures period, the, let's say, increase the emissions from the power plants, especially the thermal power plants, increases by about, let's say, 3% per degree of temperature increase. So because of the increase of the temperature, we have much higher emissions from the power plants. So there is an important impact of urban overheating on energy, and there is an important impact of urban overheating on environmental quality. But in my opinion, one of the major, let's say, problems, which is associated with urban overheating, it has to do with, let's say, the vulnerable population, low-income population. We know very well that low-income population is living in houses of low quality, not well protected, and because of that, really, they are the first victim of urban overheating. Do we have enough studies that shows really the impact of urban overheating on, let's say, vulnerable population? Yes. During the very last years, there are a lot of studies, performed experimental studies. I'd like to show you a study we performed 10 years ago in Athens, Greece, involving about 400 low-income houses during a heat wave. You see the evolution of the indoor temperature. Before the heat wave, indoor temperature was, let's say, 27 degrees, no problem. At the end of the heat wave, 5 days, average indoor temperature was 33 degrees. We have more than 3 days with temperature above 35 degrees in many buildings, and many buildings presented, temperature close to 38, 39 degrees. We have also collected data from about 110 low-income houses in Western Sydney. And you can see from this graph last year that not during a heat wave, during, let's say, a normal reference weather, indoor temperature in low-income housing in Western Sydney was as high as 40 degrees. And, average temperature was much higher than 30 degrees. And this brings us to the more important problem associated with urban overheating, the problem of health. Heat-related mortality increases above the threshold temperature. This is very well known. Is it so simple? No. It is a very complicated relation. It's not a linear or, let's say, an easy deterministic correlation between the threshold temperature and heat-related mortality. There are many parameters that affect, this association. And first of all, demographic, the age of people, for example. The several other issues that have to do with, let's say, the local health and things like that. Socioeconomic issues, deprivation levels, health infrastructure in the different cities. When all these issues are taken into account, and we have a lot of data, and we have studies from more than 100 cities in developed countries around the world, all the study shows that heat-related mortality in, let's say, the overheated part of the cities is 6% higher than heat-related mortality in the coolest part of the city, in average. And this applies in developed countries. Unfortunately, because of the lack of statistics, we don't have data for less developed countries, where I'm afraid that the situation is much, much worse. So given that, I'd like to show you this association between, let's say, temperature and heat-related mortality. I'd like to show you some data from a recent study in Europe, where it shows the, let's say, the association between ambient temperature or apparent temperature in the horizontal axis and the, let's say, logarithm of the mortality rate. And this graph is Athens. You see that above, let's say, 30, 31 degrees, heat-related mortality is increasing almost exponentially. The same for most of the Southern European, let's say, cities. And in this case, the threshold temperature above which heat-related mortality is increasing in, let's say, cooling-dominated climates is between 29 to 32 degrees. But this is not the case in cooling-dominated climates, London, Helsinki, let's say, Stockholm, Copenhagen. In this case, in these cities, heat-related mortality is increasing above, let's say, 21 to 23 degrees. So we don't behave the same way. Why? This has to do with our adaptation. So all those that they say, overheating is good for us in the north because we may have higher temperature, they don't really take into account that this may affect mortality and health problems in the area. What happens in Sydney, for example? We have performed studies trying to associate heat-related mortality with, let's say, overheating in Sydney. And I'd like to show you the distribution of heat-related mortality in, let's say, the city of Sydney during the period of 16-17, where we had more data. You can see that in the northwestern part of the city, where temperature is to above during, let's say, the summer period, up to 9 degrees higher than in the eastern part, the coastal part of the city, heat-related mortality per 100,000 people is almost 3 times higher than in the coastal area. So there's a tremendous, let's say, increase of mortality and a tremendous penalty which is imposed to the local population because of the heat-related mortality. But it's not just the outdoor, let's say, environment that affects mortality. It has to do with the association of the quality of, let's say, the indoor environment. A recent study that has been performed in London by UCL showed that while, let's say, the mortality or the risk of mortality because of the outdoor, let's say, overheating is 6.1 deaths per million, when this is associated with low quality of the indoor environment, it is increasing by a factor of 4 and goes up to 23.5. So once really we discuss and we, let's say, study the problem of overheating on health, we have to consider in parallel and in a combined way the, let's say, quality of the outdoor, but also of the indoor environment. This was the second part. What happens, regarding the impact of urban overheating in energy, environment, survivability, health. These are the bad news. Do we have good news? Yes. During the last 10, 15 years, we have made a tremendous progress regarding mitigation. We have made a tremendous progress in developing technologies knowledge to decrease the temperature of our cities. And we have developed a lot of new technologies, for example, evaporative, cool roofs, vegetation, and many, let's say, new technologies, new, let's say, mitigation strategies that are implemented, which really have tested in many cities. So we have a lot of knowledge about, let's say, the efficiency of these mitigation technologies. I will concentrate in two specific, let's say, technologies, mainly the use of materials, and second, the use of greenery. During the very last years, regarding materials, the development of materials and the implementation of materials in cities, which may decrease the temperature, of the urban environment. And these materials really contribute tremendously to decrease the temperature. I like to go and present you the progress we have regarding these materials. But before really moving and presenting you the efficiency and the characteristics of these materials, I'd like to tell you that we have in the very recent years a tremendous progress on the understanding and documentation of urban overheating. We have new techniques using UAVs, drones, using many other techniques to map urban overheating. For example, you see a picture of the urban overheating surface temperature in the city of Alice Springs in Australia. And this is a resolution of 5 centimeters by 5 centimeters that is collected by our specific, drone. So we know by collecting this information where we have to intervene. So we can avoid to have horizontal actions that may increase the cost and may decrease also the efficiency. Also, we know exactly, and we can convince by using these, let's say, videos, these graphs, these figures, all the decision managers and the decision makers where they have to interact. So we can document our work. This is a tremendous, let's say, development. But let's go back to the materials. So I like really to present you the development of infrared reflective color materials, something that has happened 15 years ago, materials that are used in the urban environment, which really have any color. You see, for example, in the right part, the standard and the cool materials, but present a much higher reflectivity in the infrared. We cannot see it because our human eyes cannot really understand the infrared. So in this case, we can increase tremendously the reflectance of the materials without changing the color. These materials are really commercialized, are available all over the world, and we know that present, and you see, for example, some pictures, up to 15 degrees of lower surface temperature than, let's say, the conventional materials of the same color. Are these materials available, and do we have enough evidence about their performance? Yes. As I mentioned before, there are more than 150 companies all around the world that they commercialize these materials, very high efficiency materials. And actually, through a study that we performed for the Department of Industry here in Australia, we have calculated the efficiency, or let's say the potential of mitigation in the 5 major cities, of Australia: Sydney, Melbourne, Brisbane, Adelaide, and Perth. As you can see from these graphs, during, let's say, the peak summer period, 2 o'clock in the afternoon, by using cool roofs, by using materials, of higher reflectivity, just in our roofs, not in the pavement, we may decrease the peak temperature up to 1.5 degrees, in some cases, for example, in the case of Brisbane, up to 1.8 degrees. This is a tremendous, let's say, potential for mitigation. But this was developed 15 years ago. This is something which is well known, and we have many applications, more than 400 applications around the world. What about the newest, developments? The use of thermochromic materials, materials that they can change color as a function of temperature, is something that really has studied many times. These materials may be, let's say, of any color during the winter period, may absorb heat, because we may wish to have, let's say, absorption of heat during the winter, and became white or at any color during the summer period, so they became reflective. So these materials may, let's say, absorb heat during, let's say, the winter period and may reflect heat during the summer period. We have developed these materials and we have tested these materials, and we can achieve up to 21 degrees lower surface temperature. If you don't believe me, you can see the thermal graph in the lower right part, because, you know, of the thermochromic materials. The main problem of the thermochromic materials is that present a very serious optical degradation. After 5-6 months, they lose their ability to change the color. So we have concentrated on the development of methodologies to improve their, let's say, aging efficiency. And by using some optical filters, we have really succeeded to extend the, let's say, efficiency of these materials and let's say, the optical performance of these materials up to 3 or 4 years. And these materials are now almost commercialized and I expect in the near future to be, let's say, in the market. However, there is a tremendous potential on thermochromic materials, materials that change the color, once we're using photonic crystals and plasmonic. These, you know, materials, photonic crystals and plasmonic, some of them, they are based on temperature-sensitive physical or optical property variation, and also may change the color without really having problems of photodegradation. Actually, there is a lot of research on it, and we expect that in the near future, we may have thermochromic materials based on photonic and plasmonic crystal, which really do not present any problem of aging. However, the real, let's say, revolution in terms of building materials for mitigation, it has to do with the so-called radiative cooling materials, photonic materials. These are materials that have been developed that present a very high reflectivity in the solar spectrum, 96, 97%, but they present a very high emissivity in the so-called atmospheric window, 8 to 13 microns. The atmospheric window is really a part of the atmosphere which the radiation which is coming from the Earth is not absorbed. Let's say, is transparent, the atmosphere, and the, let's say, radiation which is emitted at this wavelength may escape to the space. In this case, by developing materials that have a very high reflectivity and a very high emissivity in the atmospheric window, we don't absorb the heat, and we, let's say, send the excess heat to the space. We don't send it to the atmosphere and return back. So these materials, which really present a high resolution, a high revolution during the very last years, are developed now, and some of them are commercially available. I'd like to show you the development we have achieved here in UNSW during last summer in Alice Springs in the Australian desert. Temperature was about 40 degrees. Solar radiation was about 1,100 watts. These materials, you see, for example, the results presented about, let's say, 15 to 20 degrees lower surface temperature than the ambient one. These are materials of, let's say, natural air conditioning. So imagine you have a material which presents 15 to 20 degrees lower surface temperature than the ambient temperature. So these materials present a tremendous potential for, let's say, cooling and mitigation in our cities. Do we have enough applications? We started a very big application in Riyadh, Saudi Arabia, where we are, let's say, responsible for the whole mitigation project of the city. And by using, let's say, these super cool materials as are known, we may decrease the peak temperature of the city during, let's say, the peak temperature up to 4 degrees. So this is very important. This is a tremendous potential. And this is a study that is performed together with Berkeley laboratory, let's say, in the United States. But also, we performed the same study, and there is, you know, a high potential for application in a tropical city, Calcutta. And you see also the results. you see that by using these materials, it is possible to decrease the temperature of the city up to 4 degrees or sometimes 5 degrees. These are the advantages of supercool materials. Unfortunately, when these materials are applied in heating and cooling dominated climates, I mean in cities which need both heating and cooling, in this case, we may have a problem of overcooling during the winter. And we don't like this. We don't like to increase the heating demand of our cities. Simulations that have been performed for the city of Calcutta shows that once these supercool materials are applied in the urban environment, may decrease the temperature of the cities during the winter up to 2 degrees. This is something that we don't like. To face this problem, we have developed some modulation techniques. So we have developed materials which really have a very high reflectance during the summer period, but during the winter period, the reflectance is decreasing, is up to 10%, so it is absorbing. And also during the summer period, these materials present a very high emissivity to the atmospheric window, but during the winter period, the emissivity becomes very low. So these materials are very much adapted to the local conditions. By using these modulation techniques, we may achieve to decrease the peak temperature of the cities during the summer up to 4 or 5 degrees, and at the same time, increase the temperature of cities up to 2 degrees during the winter. So these materials are win-win for our cities. So photonic materials combined with advanced modulation techniques may be the future really for our cities. We try to improve these materials by using, let's say, advanced techniques in order to improve further their performance. And we are testing different, let's say, technologies in order really to decrease the cost. The cost is not so high, but at the same time, really improve their efficiency. A third technology that I like really to refer and show you, it has to do with the use of fluorescent cooling materials. Quantum dots, very small semiconductor particles, present something very important. In reality, do not absorb heat. While, every material absorbs heat when radiation falls on the material, part of the radiation is absorbed. In quantum dots, the radiation is absorbed, but it is immediately re-emitted, or part of the radiation is re-emitted as fluorescent radiation. In this case, the energy balance of the materials is very close to zero. So these materials present a very high efficiency for mitigation. We have tested all these materials, and we have developed initially, let's say, some mitigation products for cities using just fluorescent techniques really for mitigation. We have achieved to decrease the temperature up to 2 degrees, which is not so high. At a later phase, when really we combine it with cool techniques, I mean infrared reflective materials, we succeeded to decrease the surface temperature of the materials up to 20 degrees. So these materials present really a very high efficiency for mitigation. And we expect that, the use of a new, let's say, family of materials, anti-Stokes materials, materials that emit more than what they absorb, yes, it is possible to emit more than what it is absorbed. So have a negative, let's say, balance. In this case, our calculation shows that these materials may decrease their surface temperature up to 35 degrees below the ambient one. So there's a tremendous potential there. We have a research project and we work on it. For practical applications, we work and we're developing now together with a big Australian company of coatings, some, let's say, coatings, paints, which are based on radiative cooling techniques. And according to our fresh data and simulations, we may decrease the surface temperature of, let's say, the materials or of the building structures up to 15 degrees. So by having a radiative cooling paint, and there are many other products also in the market, especially in the United States, we may, let's say, decrease the surface temperature of these materials up to 15 degrees. These are very cheap materials that really may help tremendously to decrease the temperature of our cities. A second problem associated with the use of, let's say, photonic materials is that they present very high reflectivity, 97%. So these materials cannot be used on vertical facades, may create glare, may create contrast. You cannot have these materials on streets, on pavements. So what about the development of colored materials, low reflectivity materials, no problems of glare, but of high efficiency? So what we're developing now, and we have a very big project on it, is colored infrared photonic materials, which really present a low reflectivity, but they emit most of the radiation through fluorescence. It is, let's say, a combination between photonic and fluorescent materials. These materials, you know, may present a low emissivity, a low reflectivity, a high emissivity, and a high fluorescence. So we substitute the cooling effect of high reflectance with the high, let's say, emission of fluorescent radiation. In this case, we may have, let's say, very high efficiency. These materials are not yet developed. We work on it. We expect that during next year, we will have, you know, all these materials ready. What is the state of the art regarding the temperature decrease because of the photonic materials? Actually, we have from the existing applications up to 15 degrees lower surface temperature, which is tremendous. It's a natural air conditioning. And of course, under, you know, specific conditions, no convection, they have achieved in the United States to decrease the surface temperature of the materials up to 40 degrees below, you know, the ambient temperature. We don't need it in the built environment because there will be other problems. But 15 degrees below the ambient temperature, combined with modulation techniques to avoid overcooling in winter, really, it's a fantastic solution. So if we try to conclude about materials, and we see the history of building materials in the built environment, we started, let's say, some years ago with normal conventional materials presenting this type of temperature, and these are experimental data. And gradually, we decrease the temperature, and we are here at this level, and we are able really to decrease the surface temperature of our, let's say, cities up to 15 degrees below the ambient temperature. This may have a tremendous impact on the temperature. So once, let's say, these techniques are developed, we may have implemented a serious decrease of the temperature. And let's move to the second important, let's say, in my opinion, technology, or you like technique for, let's say, mitigation, the use of greenery, of urban greenery. If we increase the green infrastructure of our cities, we may have a lot of benefits. We may decrease the temperature and many, many other, let's say, benefits. Do we have enough knowledge about, let's say, the impact of greenery in our cities? Yes. There are hundreds of studies that really shows the association between the increase of the green infrastructure and the ambient temperature. And in this graph, you see most of the studies plotted together. The lower part, the upper part, it shows the association between the night temperature and the increase of the green infrastructure and the night temperature. So the use of greenery during night may decrease the temperature of our cities up to, let's say, 1.5 degrees. The efficiency is much lower during the daytime, can be 0.6, 0.7 degrees. I can explain you why, but we don't have the time. Another issue that has to be considered once, you know, greenery is one of the solutions in cities, it is that our, let's say, vegetation presents, you know, a decrease of evapotranspiration or even a zero evapotranspiration above a threshold ambient temperature. Why? Because trees, they like to keep their sap. So they stop really the evapotranspiration, they don't contribute anymore to heating, and because their, let's say, leaves are green, dark green, they may present higher temperature than the ambient one and may contribute to heating. This is the reason that in many urban parks, during heat waves, the temperature is higher than outside, the urban parks. These are the results of a study that we performed, experimental study here in Sydney with eucalyptus. And you can see, for example, that above 30, 31 degrees, the evapotranspiration really of the trees has decreased tremendously or has become almost zero. Another important issue that has to be considered with greenery, it has to do with the BVOCs, which are emitted by some of the plants. We have really seen that by increasing the green infrastructure in some cities, without taking into account the type of trees which are used, we may have a very serious increase of the concentration of pollutants and a very serious increase of the concentration, of ozone. Also, we have to consider the use of water. And in many cities, and especially in dry cities, the use of non-irrigated vegetation may increase the temperature. This was the case of Los Angeles, and this is the case also of Riyadh. So where we are, 20 years ago, we started with some, let's say, reflective materials, wide reflective materials, and we have succeeded to decrease the temperature up to, let's say, 0.5 degrees. Later, by using infrared reflective materials, we, let's say, decrease temperature up to 0.7, 0.8 degrees. Gradually, the use of the materials that I have presented you, photonic materials, fluorescent materials, etc., have contributed to be able to decrease the temperature of our cities up to 2.5 degrees and decrease also the surface temperature up to 15 degrees. Now, in our days, there are more than 150, maybe 200, let's say, large-scale mitigation projects all around the world, where, let's say, the peak temperature has been decreased by 2.5 degrees, and we expect that in the near future, we'll be able to decrease the peak temperature up to 4 degrees. This may have a tremendous impact on the energy demand. The study we have performed for the Department of Industry here in Australia shows that for specific type of buildings, for example, a non-insulated housing or office building, may decrease the use of cool roofs, may decrease the need for cooling up to 40 or 50%. This is something really tremendous with such a simple technology. Or at the same time, may decrease the peak electricity demand in the different parts of Australia up to, let's say, 20, 25%, which means that really we need less power plant, we need less pollution, less emission. And this is very clear once really we see the curve between the ambient temperature and, let's say, the decrease of the peak electricity demand in our cities. And you can see that once the temperature is reasonable, 20x, 26, 27, 28, up to 30 degrees, the peak electricity demand may decrease up to 30% because, of the use of cool roofs. But it's not just that. The use of cool roofs improves also the efficiency of the air conditioners. Why? Because we have less ambient temperature. So our study shows that really, once we are using, let's say, cool materials in our buildings at the city scale, the total benefits may be, energy benefits may be of the order of magnitude between 50 to 59 degrees. At the low temperature, let's say, in low albedo cities, in cities where only, we apply cool roofs at the building scale, the benefits may be of the order of magnitude of 4 to 48 degrees. And the increase of the efficiency of the air conditioners because of the cool roofs may be of the order of magnitude of 3 to 8 degrees. This is a map that shows the benefits in gigawatt hours in the different parts of Sydney once cool roofs really are applied, which means that by using cool roofs in the total energy consumption of Sydney, we may have a decrease of the order of magnitude of 32%, which is a tremendous real decrease. Similar, let's say, data have been, and results have been obtained when we calculated the same thing for the city of Riyadh together with Berkeley Laboratory, using, let's say, about 1,300 buildings, real buildings in the city center. And the energy consumption was really tremendous. So if we try to conclude on it, and we try to see the future scenarios, actually, in Sydney, the energy consumption for cooling for, let's say, a house, a traditional house, is shown in the red bars. And this is the yellow one, is the heating one. By 2050, if we do nothing, the energy consumption for cooling will increase by 3 times without really having a tremendous decrease of the heating need. In case that we apply mitigation, the existing mitigation techniques, we may have a very serious decrease of the cooling demand up to 40%, and let's say not an important decrease of the heating. But once we apply combined mitigation and adaptation technologies, which means better urban environment of lower temperature, together with better buildings, then by 2050, we may almost minimize, despite the climatic change, the energy demand for heating and cooling. This is a tremendous, achievement, and shows that there is hope really for the future. What about, the use of cool roofs and cool materials on PVs? We have seen, for example, that the use of cool roofs on, let's say, PVs may increase their efficiency. But on the other hand, we have to consider that the use of PVs, which really contribute to heat the urban environment, may increase the urban temperature and the ambient temperature. These are the results of a simulation we have performed for the city of Sydney, together with the University of Calcutta, that shows that once we increase the concentration or the installation or the implementation of PVs in the city, we may have an increase of the temperature of the city up to 1.5 degrees. So in this case, the use of PVs in our cities is something that has to be considered. What's about the economic, let's say, benefits of cool roofs? We have calculated the economic benefits. Once cool roofs are used and cool materials and mitigation strategies are used in Australia, the benefits may be many billions for the whole country for different reasons. But at the same time, we may create some million of new jobs. And of course, I don't like to go through all these numbers. You can really download all this information. So it's a win-win. We may create jobs and we may, let's say, have a lot of positive impact. What about the impact of mitigation on health? There are many studies that show that by increasing, let's say, the albedo of cities, we may have a decrease of the heat-related mortality up to 1.8% per 0.1 increase of the albedo. And the studies that we have performed in Sydney, it shows that while the summer heat-related mortality is 440 per 100,000 people during the summer, this, let's say, the application of cool roof may save up to 82 lives per year, let's say, because of the lower temperature. The same happens with, let's say, the use of greenery. And several studies have shown that it is possible to decrease heat-related mortality up to 3% once we decrease temperature by 0.1 degree. So to conclude, we'll have a serious problem. Our cities are up to 6 or 10 degrees of higher temperature. This has a tremendous impact on the energy consumption, up to 100% higher energy consumption. A very high impact on heat-related mortality, up to 300%. A very high increase of the peak electricity demand. This is the actual situation, the future. We are able now to decrease the temperature of our cities up to 2.5 degrees. We have more than 200 projects. And we are confident that in the near future, we may decrease the temperature up to 4 degrees. We may decrease the heat, the energy consumption up to 50, 60%. We may decrease heat-related mortality up to 40% and may decrease the peak electricity demand up to 10%. But in order really to achieve that, we have to work in a synergetic way. We cannot really continue to work, every one of us, on a separate discipline. The energy experts, they do the energy studies. The health experts, the epidemiology experts, they do their research. The pollution experts, they do their research. We have to integrate. We need really to work in a synergetic way, and to really consider mitigation of our cities, we have really to integrate all the different disciplines which have to do with energy demand, the energy generation, health, pollution, vulnerability, economy, together in an holistic and integrated way. Thank you so much.
Thanks, Professor Matt, very much for your wonderful and fantastic talk. Matt, there have been many questions coming through the chat and also during registration process. First question is, how important is landscaping around high, mid-rise buildings in mitigating the heat island effect? Does this landscaping need to be at ground level, or is vegetation at upper levels also useful?
Can you repeat it, Lan? Because can you repeat the question?
Sure. How important is landscaping around high or mid-rise buildings in mitigating the heat island effect? Does this landscaping need to be at the ground level, or is vegetation at upper levels also useful?
Yes, thank you. In mitigation studies, we have to apply a medical procedure. In order to give medicines, we have to know the problem of the sickness. So first, we have really to scan. Which is the reason that around, high-rise buildings, we may have higher temperature or discomfort? So once this is well understood, then we may plan, let's say, the solution. If the reason of the overheating is the, let's say, anthropogenic heat, the use of, let's say, reflective materials or cool materials may not help at all. So the answer is the following. First, understand the reasons that really gives you the problem, and then find the solution. We cannot give any kind of medicines to any kind of sickness. For example, if someone is suffering from tuberculosis, we cannot give him, medicines for cancer. So the problem of overheating in the different cities is not the same. If someone has applied, successfully a certain mitigation technology in London, perhaps the same exactly mitigation procedure in Riyadh or in Sydney may not give results at all, because the reason of the overheating is completely different. So the conclusion is, apply a scientific approach, not an empirical approach. Understand the problem, understand the physics and the characteristics of the problem, and then define and, let's say, design the proper solution.
Thanks, Matt. The second question is, last week, the EU Commission said they are planning to mandate rooftop solar on all new residential and commercial buildings by 2029. Are policymakers in the EU and elsewhere aware of the progress being made on cool roof research, as well as the potential of cool roofs and the pavements to reduce aggregate air conditioning energy use in cities?
Thank you. This is a very interesting question, The use of PVs in cities, I think that with all the results we have, the very recent study, very recent years, shown an important increase of the ambient temperature, especially in cooling-dominated cities, in, let's say, overheated cities. In a non-overheated city, perhaps the problem is not so important. But in an overheating city, applying and implementing a lot of photovoltaics is something that we have to consider. It increases the temperature. Actually, as I showed you before, for the city of Sydney, by implementing, up to 75% of photovoltaics in our roofs, may increase the temperature up to 1.5 degrees. This may, let's say, increase the energy consumption for cooling up to 25% because of the temperature increase. So a high part of the benefits from the photovoltaics is lost. We will present more data on it. So photovoltaics is a wonderful solution. It's a solution that really provides free electricity, provides, electricity at low cost, if really storage is not used, because if storage is necessary, then we have a problem. So we have really to consider the use of photovoltaics, and I'm very positive to use photovoltaics, but between us, I would really prefer to have most of the photovoltaics out of the cities, not in the cities. I would really prefer to have farms of photovoltaics out of the cities, because this may provide, a lot of electricity, perhaps lower cost, but will not really create problems of overheating, especially in cooling-dominated climates. This is my opinion. I know that many people, they have let's say, another opinion, but I think that in the near future, the increased implementation of photovoltaics, especially in overheated cities, will have a serious problem for the built environment.
Thanks, Matt. Next question is, does the application of cool roof present acceptable temperature decrease and energy demand in high-rise buildings typologies, which are mostly located in the CBD?
Yes, the study we have performed for the Department of Industry has evaluated 17 types of buildings. You can download this, let's say, study, or you can follow, let's say, the presentation we have next week about, the use of cool roofs in Australia. The energy impact of cool roofs in high-rise buildings is, of course, let's say, limited. Can be, let's say, as low as 5%, 6%, 7%. In low-rise buildings and buildings without insulation, the benefits may be as high as 50%. So for high-rise buildings, the use of cool roofs may be, let's say, the energy benefits from cool roofs may be, of course, limited. But it's not only the benefit to the building, it's the benefit to the environment that decreases the temperature, and so it decreases in an indirect way the cooling need of the buildings, even of the higher, let's say, the high-rise buildings. Just to understand, while the direct, let's say, benefits of cool roofs in high-rise buildings is close to 3 to 5%, once this is combined with an extended implementation of cool roofs in the city, the benefits may be of the order of magnitude of 25%.
Thanks, Matt. The next question is, can these methods be applied to existing buildings, or are they only for new buildings?
Both can be in any type of buildings. Yeah.
Right. Next question. Are you sharing your findings with the 3 levels of government here in Australia?
Can you repeat the question?
Are you sharing your findings with the 3 levels of government here in Australia?
We have communicated our research, to everyone. We have performed many studies for different, let's say, for the Department of Industry, for, let's say, different local governments, for different councils. There are many studies, and we hope to have more, let's say, results and more, let's say, demonstrations in Australia. In Australia, we have, for the time being, a lot of studies, but not really important implementation. So I hope that in the near future, we will have real results from, like in Europe, for example, in the United States, that will show the potential, of mitigation. But as, let's say, researchers or scientists, we are, let's say, almost obliged to communicate our result to, let's say, the decision makers, and also to the scientists and everyone trying to influence, but we are not decision makers.
Thanks, Matt. Next question. What do you see as the single largest impediment to changing consumer behavior in selecting better performing outcomes?
Yeah, human behavior, change the human behavior towards, what? Let's say, ask for more green, ask for more, let's say, greenery in cities, ask for, let's say, more, let's say, reflective materials. First, I think the population has to know. And most of the population does not really know the impact and the potential of the different mitigation technologies. Unfortunately, we live with myths. Most of the people believe, for example, that by increasing the greenery in Sydney, planting 5 million trees, we may face the problem of overheating. No, will not face the problem of overheating. Will decrease temperature up to 1.5 degrees, will increase tremendously humidity, ozone, and also will increase up to 25% more the use of, let's say, water. So the problem is the right documentation and the proper information to the people. So people has not for the time being the proper information. Has not the proper information. So we cannot ask them to, let's say, demand for solutions if they don't have the proper information. The same happens also with the decision makers. They prefer, simple solutions, easy to digest solutions. Okay, let's plant trees. Let's change the roof, the color of the roofs. They don't really follow a scientific approach. They don't understand the problem. They don't understand the characteristics of the problem, and then fine-tuning, solutions that really solve the problem. But gradually, we have more and more results, better applications all around the world that shows really successful projects. I had the chance some years ago to, let's say, coordinate the implementation of about 80 large-scale mitigation implementations in Europe. And I have to tell you that out of the 80, about 15 were very successful. The rest were less successful. And this because, of the way that really the design team has really approached things. The message is very clear. We have the scientific knowledge. Apply the scientific knowledge. Don't use empirical ways. Don't believe in myths. You cannot really apply traditional Chinese, let's say, medical procedures to solve the problem or to cure cancer. The problem of overheating in cities is a cancer. You need to apply very specific medicines, not simple solutions. And these specific medicines, these, let's say, advanced technologies are almost available. So stop really believing in myths, stop really believing in empirical ways. We have to use scientific knowledge and the proper, implementation and the proper policies in our cities should be based on real knowledge.
Thank you so much, Matt. And also thank you for your questions. We will ask Professor Matt to answer your questions and then send to you through email. Thank you very much for joining us today. The second high-performance architecture webinar will be in June, presented by Scientia Professor Dale Prasad, the former CEO of CRC for Low Carbon Living. And his topic is Race to Net Zero Carbon Buildings 2030. The registration link is now available in the chat. So thank you so much. And we look forward to seeing you in the next webinar in June. Bye-bye.
Bye.